Hello everyone, I'm Peng Gao from the South China University of Technology. It's my pleasure to introduce my research work with you. The prediction of the chemical shrinkage of potassium cement by using Hammer's 3D model. Here are the list of contents. We have 5 parts. First is introduction. The chemical shrinkage is defined as the volume difference between the reactants and the products with ongoing hydration of cement. Chemical shrinkage is very important for us to evaluate the self-desiccation and cracking risk in cement-based materials, because it will cause the self-desiccation and which will cause the autogeneous shrinkage. The process to calculate the chemical shrinkage actually it's very simple for us. It seems very simple for us. First, we can obtain the degree of hydration of cement by using Hammer's hydration models such as Hammer's 3D, VOIC, and other hydration models. And then, by considering the stoichiometry of these components in potassium cement, we can calculate the reactants and the product's volume, and then we can use them to calculate the chemical shrinkage. However, in different research, the stoichiometry might be different. The topic of this study to determine the stoichiometry of these monomers, particularly the C3A and C4S, because these two are affected by the hydration process of the cement. For the C3S and C2S, we're using these two equations to describe the reactions between C3A and C3 and water. And for the C3A and C4AF, actually we have 6 equations. And the problem is how to determine the amount of C3 and C4F in different equations, although these equations depend on the actual content of gypsum and AFT. This is the modeling group. First, we have the inputs, including the mineral compositions, the particle size distribution, water-to-band ratio, and by using Hammer's 3D model, we can obtain the degree of hydration of the individual components of cement at a certain hydration step. And by using a discrete algorithm we proposed in this study, we can determine the stoichiometry of the individual components at a certain hydration step, which can be used to calculate the outputs such as the volume evolution of phases and the chemical shrinkage. Here is the method. As you can see in this figure, we classified the reactions of the C3A and C4F in 3 stages according to the actual content of AFT and gypsum. In first stage, the gypsum is in the system. In stage 2, gypsum is consumed. And in stage 3, the AFT is consumed. The problem is that although we can use the model to predict the hydration degree of C3 and C4F, but however, the hydration time is normally discretized in the hydration model, and the boundary time, for the different stages, might be between the hydration steps, as you can see this figure. For example, in first boundary time, it might be step I and step I plus 1. So for us, it's difficult to using the hydration model to predict the degree of hydration of the C3A and the C4F in the boundary time. So I proposed an algorithm to deal with this problem in this study. The first boundary time, the condition of first boundary time, of course, as it means the consumed gypsum is equal to has a relationship between the consumed C3A and C4F. So we have this equation 9. and by establishing the degree of hydration of C3 and C4F, we can have equation 10 and equation 11. And the key point in this study is to solve equation 9 to equation 11. To solve this equation, we assume that the ratio of the degree of hydration of C3 at first stage to the degree of the hydration of C4F is close to this ratio at the previous hydration step, because this ratio can be obtained by using a Helmholtz-Schrader model. So we can have this output. We can calculate the degree of hydration of C3 and C4 at the first stage, the boundary time, and then we in the second boundary time we have this condition: they consume the FT is equal to the produced FT at first stage. So we have this relationship. Of course, to solve this equation, we are also assume that this ratio equal to the ratio of C3 and C4F at the previous hydration step. So we can calculate the degree of hydration of C4F and C3 at the second boundary time. Here are the results and the discussions. You have these input parameters, the particle size distribution, and then we simulate the degree of cement in a cement paste with different water-to-band ratio, 0.3 and 0.4. And then we will have this volume evolution of phases. As you can see, the red line means the boundary times. At the first boundary time, the FT before the first boundary time, FT the amount is increased. After the first boundary time, the amount of FT is consumed. Also, and the water-to-band ratio will affect the boundary time. And as you can see, the first and second boundary times for 0.4 will be earlier than that in the water-band ratio 0.3. And then it's the simulated chemical shrinkage of the cement. As you can see, we have the simulated chemical shrinkage are very close to the experimental results. Here is the comparison between our research with other equations. If we use the traditional equations such as Pauling equation, we will find that the degree of hydration is linearly increasing with the chemical shrinkage is linearly increasing with the degree of hydration of cement. However, for our study, we found that this is not a linear equation. Conclusion. Here we describe a discrete algorithm to deal with the stoichiometric conversion of C3A and C4F with the progress of the hydration of cement. And then we found that the nonlinear relationship between the chemical shrinkage and degree of hydration of cement was mirrored by our study. Here are the acknowledgements, and thank you very much for your attention.